So I'm going to talk today about basically what we did with the last year of the lecture, which is phase transition. More specifically, phase transition in eigenmodels. So I will go through the derivation of some of the things that we did like quickly, and then we're going to solve like a bunch of typical test type questions. And that's it. So for one-dimensional eigenmodel, so in general, how do we define phase transition? So we usually look at some specific order parameter. In the case of everything we do, it's going to be the magnetization. So if we look, for example, at the magnetization as a function of the magnetic field, so we usually expect if you don't have any external magnetic field, the system is completely symmetric. We expect the magnetization at the zero magnetic field to be zero, because there's nothing that creates any bias. And then when we increase the magnetic field, we're going to have larger and larger magnetization, and the same for the negative field too. So we define phase transition where we have some temperature that we call it the critical temperature, where below this temperature, if we look at the same function, we're going to have something that looks a bit different. So we're going to have some jump in the magnetization. So even if we don't have any external force on the system, we're still going to have a symmetry break-in of what happened to the order parameter. So below this critical temperature, we're going to have a finite magnetization even for zero magnetic field, and above this critical temperature, the system going to behave in like the more intuitive, disordered way. So you saw that when you did in the homework the Monte Carlo simulation. So you saw that like below some temperature, you're going to have, so you look at like magnetization as a function of the temperature. So for lower temperature, you had some finite magnetization. For higher temperature, you had zero magnetization. And in between, you had something, depends on how accurate the simulation was, but you had this distinction. So this is the general definition. So what happened in the one-dimensional case? So let's look at like a Ising chain. So we have a bunch of like one-dimensional spins. So some of them in the ground state, all of the spins going to head the same direction, right? So all of the spins going to head up, for example.
הרב שסידרת את זה מחק, תקבלה אחד למד מונט קרלו. זה בעצם היה לכל טמפרטורה שאנחנו נקרא, נכון?
That was what you got in the homework.
כן, זה נכון. היה כמובן שדה מגנטי.
So you have one state, which is all of the spins going to head the same direction, all of the spins are aligned. And let's compare it to another state where some of the spins heading up, and then some of the spins are heading down. So all of the spins in that direction are going to be down, and all of the spins in that direction are going to be up. The board is like limited, of course. So I have here what we usually call a domain wall. That it's not a real thing that exists, it's just the way we represent the separation between the spins up and down. So the system wants, the physics want to minimize the free energy. which is defined by E, which is the energy that we usually associate with the Hamiltonian, so the energy that we usually call just energy, minus the temperature multiplied by the entropy. So this is the thing that we want to find the minimum of. So the system going to choose whatever system is going to have a lower free energy. So what's going to be the difference in the energy between that system and that system? It's only going to be a result of those two spins, because I have the interaction term of minus J Si plus 1, right? So I have some energy from this, I have some energy from those, and like the only difference is what's going to happen here. So I have contribution of minus 1 multiplied by 1, so overall J. So the difference in the energy going to be 2J. That's the difference between the two systems. Now what's going to be the difference in the entropy? So the only difference is the existence of the domain wall. So the only variable is the location of the domain wall. So I have n possibilities to where I'm going to put this domain wall. N is the number of the spins. So the difference in the entropy going to be, let's say, to be fair, proportional to the log of n. Or line. It's infinite.
אז רגע, אז למה יש לך 2?
It's n where n go to infinity.
רגע, אז למה יש לך 2?
Because it's only related to that.
כן, אז יש לך אינטראקציה אחת, כאילו.
No, here you're going to have...
אוקיי.
Okay. This is just the difference. So overall, the difference in the free energy between that and that is going to be 2J minus the log n. So in order for the system to undergo a phase transition, so to choose the upper state rather than the lower state, that difference needs to be larger than 0. So we said that we take a very large system, the statistical physics, that's what we do. So if n go to infinity, that expression can only be larger than 0 if t is equal to 0, right? Because logarithm of n always going to be a very large number. So the only way that will happen is if t critically equal to 0. So if you would try to do a similar simulation to what you did in the homework for one-dimensional system, what you're going to see is that you have the magnetization versus the temperature. So it's still always going to be around 0. And then technically, where the temperature is equal to 0, you can have a finite magnetization. So at the 0 temperature, all of the spins going to align to the same direction. I think it will be very hard to actually see that in simulation, but you understand. So we can't have a phase transition in a one-dimensional Isaac model, but there is a way that we can have a phase transition if we change the interaction of the system. So in that case, we used nearest neighbors interaction. So each spin.
Why did that mean there's no phase transition?
So I want the free energy of that state to be larger than that in order to have a phase transition. So I got that the difference is 2J minus T log of n. So in order of that to be larger than 0, because J is some number of order of 1, and log of n, if n go to infinity, log of n also going to go to infinity, or some very, very large number. So the only way the first term will dominate the second term is if t equal to 0. So that's the only way that's going to be positive. Otherwise, this always going to be larger. So physically what it means is that we always going to have so we always have the energy and the entropy that like compete over what's going to happen in the system. And in the case of one-dimensional system, because the only interaction is those two spins, the energy difference is just not enough. So we want to add more energy, and the easiest way to do it is to add interaction time. So let's say instead of only nearest neighbors interaction, we have long-range interaction. So let's change that. So long-range. Okay, so now we have, let's say, one interaction term for, so this is the domain wall, so this, let's call that J1. So that's the interaction with the nearest neighbors. We're also going to have J2 for the next nearest neighbor interaction. And then we're also going to have J3, and so on and so forth. So now you see that the difference in the energy between that state and the state where all of the spins are aligned is going to be larger because we have more contribution, because that spin that is next to the domain wall also going to fill the spins that are like much farther away. So we're going to have additional contribution. So what it's going to be, so the difference in the energy. So, okay, let's see. So we have the same from J1 as before, so we have to J1. And now for, so let's put 2 outside. So for J2, we're actually going to have twice the contribution than from J1, because we're going to have one from the one next to the domain wall with this one, and we're also going to have one with this one to here. So we're actually going to have 2 multiplied by J2. In the same way, for J3, we have this one with the third one, and this one with this one, and this one, this one. So we're going to have 3 neighbors now. So 3 multiplied by J3. And you understand, the more interaction terms I add, the more spin is going to be involved in that energy. It depends on what's going to be J. So in general, so let's put here like 3 ones. So in general, we're going to assume some specific, okay, not in general actually, specifically we're going to assume some form of this coupling as a function of R, where R is the distance, so R is like discrete, like 1, 2, 3, 4, and so on. So J of R going to be something like a decay, like a power law, so R to minus sigma. So the farther away going to be, the lower the interaction going to be, and what we want to do, you already did, I'm just going to go through it, is to find what's the condition on sigma to maybe do have a phase transition in the system. Because if I have interaction with spins that are very far away, it's going to be very expensive from energy perspective to keep the system in that position where like half of the spins, but some of the spins are like not aligned.
Can you remind me of what sigma is?
Yeah, so we're going to say like it's for now just a parameter. We're going to find it. Okay.
למה אנחנו את הצורה הזו ל-J עוד פעם?
Because I want.
בגלל שזה נתן משהו מהחתיון?
It's just a general form. Okay, you want to have, you want to have something that decay slow enough, as we're going to see in a few minutes why. But like if you take something that decays like exponentially, it's not going to be enough. So we want something that also interacts. And power law is like the slowest possible. Okay, so delta E in general, if you look at what we have here, we have something that go like, we can write it as sum of R multiplied by J of R, right? We have 2 multiplied by J2 and so on. So in general, if R go like that, so this is R1 minus sigma. And we don't like to solve infinite sums because they're ugly. So we're going to turn it into an integration. So let's say this is going to be to integral from 0 to n, actually from 1 to n, but let's take 0, doesn't matter, of R1 minus sigma dr. So we're going to sum over all of the sum of the size of the system. So this is going to be 2n 2 minus sigma. Approximately. I don't care about like factors. We only care about the way that it scales with n. So okay, so now you see that the difference in the energy is depend also on the size of the system, and it's not just a number like we had before. So this is already a good sign. So the entropy not going to change because I still have one parameter, which is the location of the domain wall. So overall, the difference in the free energy is going to be so 2j n 2 minus sigma minus d log n. So now we have two options. If sigma is larger than 2, so this is going to be n to minus something, so it's going to, where n go to infinity, or where n is very large, this is going to decay to a very small number, or to 0. So in that case, we're still not going to have a phase transition. So no phase transition, because this is still going to be a small number, and this is dominate the free energy as we had before. The other case,
PT or FT? Phase transition.
yeah, PT. Phase transition.
It's no phase transition because it's small number and that's minus?
Yeah, because we want, in order to have phase transition, we want that. Yeah, so this is just, we're just going back to the same case we had before. So this makes sense. Okay, I will talk about the makes sense part later. So if sigma is smaller than is larger than 2, we're not going to have phase transition. If sigma is smaller than 2, so we're going to have n2 minus 2 minus sigma is going to be larger than 0, right? So the thing going to go. Okay. I don't like to write it like that because then you get like infinite minus infinite, but this is still going to be a very large number. Let's say that. So overall, you're going to have some value, some finite value of t larger than 0 that's going to give you it's going to give you that the free energy is larger than 0. So you're going to have some finite Tc that gives you Tf of Tc equal 0. So that's the transition point. So okay, so first point, you see that we are missing one case, which is sigma equal to 2. So I'm just going to like in very elegant way add it to here. So this is actually sigma smaller or equal to 2. So you cannot get it from what we did here because we waved our hands a lot. But basically, more clever people than me show that this is also true for sigma equal to. So this is just for you. This is just a given. Okay, you need it for that to solve. You have like logarithmic corrections and stuff like that. But this is just how it works. So this is one thing. The second thing is that you see that like sigma smaller than 2 means that you have a very slow power law. You're going to have a very small decay of the interaction, which means the spins here are going to interact with spins that are very, very far away. So the interaction is going to be very strong, which makes sense because it means that like the stronger the interaction, it's going to cost us more from energy perspective to keep the system in this disordered phase compared to the case where all of the spins had aligned in the same direction. Okay, so this is long-range interaction, and now I'm going to solve a question. Can I raise?
Okay, good.
So basically, everything that we need to know from what we did here is that part. We have sigma smaller than 2 and sigma larger than 2. So, question 1 from 2020B. So, you have a given Hamiltonian. Minus. So you have a coupling coefficient J that depends on the distance between I and J, where I and J are all of the spins in the system, multiplied by delta of sigma I, sigma J. Well, sigma I equal to 0, 1, or 2. So this is like a kind of a support model system. So the first part, so they ask what's the ground state energy of the system and what is the degeneracy. So we want to find E, ground state, and G, which is degeneracy. So, okay, so we know that the ground state of the system is going to be where all of the spins head in the same direction, right? Because of this expression here, this is one where sigma and sigma J in the same direction. So E ground state equal minus sum over J, whatever this coupling coefficient is. No one haven't told us yet what it is, and delta equal 1 because they head in the same direction, and that's it. So that's the ground state energy. We keep it in that form. So what's going to be the degeneracy? So, exactly. So we have 3 options for the direction of the spin, which is 0, 1, and 2. So either all of the spins in direction 0, or 1, or 2. So we have 3 options. So G equals 3.
למה יש מצב את האנרגיות ה-GS?
So I want to find the minimum of the Hamiltonian, and this is this is going to be where the delta equal 1 because I want all of the spins to head the same direction. So if sigma is sigma j in the same direction, this is 1, so this is just everything that's left is just the sum of j.
הסיגמה יכולה להיות רק 1 או...
It's either 0, 1 or 2.
אוקיי.
רגע, איך מוכן שאולי פה חוץ J הוא משנן אותו? או שזה...
We don't know what
כאילו אנחנו
it is.
סופרים על זה גם ככה, זה פחות קריטי לנו.
רגע, אבל הרמה יותר נמוכה זה 0, לא מחלק את זה.
No, but you have a minus. Minus something is less than 0.
ו-J הוא בהכרח חיובי?
Yeah, it's a ferromagnet. I think it's probably given in the system, but not in the version that I have. But yeah, they need to say that this is a ferromagnet.
אפשר זה לבחור בשתיים, לא?
No, but delta can only be equal to 0 or 1. Either those are like in the same direction or not. Like it doesn't matter which state they are. They just have to be in the same one. Okay, so now the question you have different options for what J is, and they ask. Okay, so let me write it instead of that. So, okay. So for each, let's call it J of R. Okay. Is the system undergo a finite temperature phase transition. So we temperature. Yeah, this is temperature. Temperature. This is phase transition. I'm out of space. So we already saw that in a one-dimensional system, this is a one-dimensional system. It also should be given in the question. The thing that's going to determine if we have or don't have a phase transition is the form of J of R. So we have like either sigma smaller or larger than 2. So, okay, so the first option of J of R they give is sinus square R over R. So this is not a power law, but we know that the thing that matters for the interaction is what happened in long distance, right? We want the fat tail of the power law with the very far away spin. So we take the limit of R large. So R is like, I don't want to say go to infinity, but just R much larger than 1, I guess. So sinus square is going to be is just going to be a number. Why the sinus is between -1 and 1, so the sinus square is going to give us 1. Order of 1. So yeah. And R going to be just R. So this is going, so we can write that as R minus 1. So if you compare that to what we had before, this is actually a case of sigma equal 1, right? And this is smaller than 2, obviously, which means we do have a phase transition. So
you assume this solution, sinus square.
this is what's given in the question.
Ah.
Yeah. Up to here it's the question, this is the solution.
איך את יודעת שהסיגמה שווה לאחד?
No, it's not equal. It's approximately where R is large. This is like order of 1.
אוקיי.
Right? The sinus is sinus go between -1 and 1. So it's just a number.
כן, אבל לא באילו מקרים אני יודע שסיגמה שווה 1.
Okay.
איך הייתי אמור
You agree that we look at R that is much large, that is just large.
אוקיי.
So we want to get to a power form because that's the only thing that we solved. So the sinus is like is look like that, right? Is just a number of order 1 divided by something that go like a very large number. So we say, okay, this go approximately like 1 over R. I don't care if it's multiplied by 2 or 0.5. So this basically go like R minus 1. Okay, so what the thing that we solved was sigma of R, not sigma, sorry, J of R equal R minus sigma. So this is the same if sigma equal 1.
עכשיו מה עוד?
Okay. So the second case is J of R equal 1 over R sinus hyperbolic of sinus of e to R. Okay, so we can rewrite that as 1, so you have R, 2, e to e R plus e to minus e R. And if we take now the limit of R being very large, so for R being a very large number, this is obviously much smaller than that. So we have approximately 2R e to e R. So this is e to minus e R over 2R. And this is obviously a very, very fast decay. Or not obviously. This is a very fast decay. This is even faster than exponential decay. So it's not even like a power law. So this is it just decay too fast. We're not going to have a phase transition. This is like we can say it's sigma larger than 2. But yeah. So again, no phase transition.
איך את יודעת מזה שזה יותר גדול מ2? אולי שזה מישהו.
Because it's exponential decay. Exponential decay always faster than power.
כאילו, כי זה אפילו לא מספר, זה אפילו יותר חזק ממספר, נגיד הייתי מקבל R, E בחזקת מינוס R.
If you have R, it's that case, which is fine.
לא, אבל E בחזקת מינוס R, נגיד לא מונה שם.
It's still going to be too fast.
כאילו זה יהיה כמו סגנון R או בסגנון R?
Yeah, everything that the decay faster than that.
Okay.
It's going to be not useful. And now the last case. So the last one, J R equal to R cubes square root 1 plus R to the power 5, R to the power of 10. So,
Sorry, where?
yes,
It's R or alpha?
R.
All
All of those are. No alpha.
No,
My
in
R
C.
maybe.
In C.
In C? Yeah, also R. Yeah, it's my R is a bit like gamma. Yeah. Okay. So
החזקה הסירית אמור להיות דומיננטי.
exactly. So if R is very large, this is going to dominate this one and this one. So this is going to be approximately r to the cube over square root of r10, r cube or i5, r to minus 2,
But it has
and
minus 2 because there is another element in the square.
sorry?
זה פחות מ... זה כאילו, את עדיין, בגלל שזה יוצא מינוס 2, את עדיין צריכה להתחשב כי זה על הגבול.
יש כבר מעבר פאזה בין השניים.
Yeah, so
But it's
yeah, if it was like we okay, what he says that it's technically decay a bit faster than r to minus 2 because I have extra terms here, but because we already say that it's also that we also know the answer for sigma equal 2, so this is like good enough for us. So this is sigma equal 2,
do we know?
which means we do have a phase dimension.
Why? I think only sigma equal to 1, no? Based on
No, we said for sigma smaller or equal to 2. That's the condition.
Okay.
פשוט בשתיים לא הוכחנו את זה. בשתיים לא הוכחנו את זה.
Okay, so this is for one-dimensional stuff. Okay, now what happens when you go to higher dimension? So we said, okay, one-dimensional, we can only have phase transition if we interact with next nearest neighbors and so on spins. But we want a bit more simple model. So let's go to higher dimension to see what happened there. So we already know for two-dimensional we have phase transition because you saw it, both in the lecture and the homework. So let's go through it quickly, just to be sure. So the argument that we made is very similar to what we said in the case of dimension 1. Here it's called Pierre's argument. I don't know how to pronounce it, I just know how to write it. So So now we work in 2D and up, but let's start with 2D. So let's say we have two-dimensional Ising model. So we have a lot of many spins up, except of one some domain in the system where the spins are going to be down.
It's the mean of
Yeah,
2D. You have two walls.
What?
You have two walls in 2D. יש על שתי קירות, כאילו.
I have 4 words. Or one very long word, depends how you look at it. So now I have a two-dimensional domain where the domain wall is going to be one-dimensional. Like earlier, we did like a line, but it was actually one, like zero-dimensional domain wall, right? It was like a point that separated the system. So now we have the contour of to go around this domain. So this is going to be domain wall. Let's say the length of that overall is L of everything.
כלומר, יש את כל הספינים מבחוץ ואת הספינים בפנים.
Yeah, so now instead of interaction between two spins, we have all of the spins that are like on the boundary of that domain. So, okay, here I only put like 6 here, so they all interact, but you can have a bigger domain and, you know, you can have more spins in between here. Not all of them going to interact, just those on the boundary. So, what's going to be the difference in the energy now? So, we said that the length of this domain wall in like spin units is going to be L. So we're going to have L spins on the boundaries, like L interactions on the boundaries. That's going to have like opposite signs. So this is going to be 2JL. Instead of 2J, we have L pairs of spins. So this is for the energy.
כאילו, כל ספין נספר פעמיים, כאילו יש ספין כאילו נגיד בפסקת פינה העליונה שמאלית, גם אם השכן כאילו למעלה, מעלה, וגם השכן משמאלו, יכול להיות שגם אם השכן מלחסונים.
No, but you only count those interactions. That's how you do in yeah, it's just regular to the Ising model. So this is like next interaction, which we don't count. So just going to be that. Okay, so the difference in the entropy. So we want to count all of the possible ways to create a L length domain wall. So this is I don't know if that's like, it's not like super rigorous or intuitive, but this is going to be some number, I call it C, but you can call it whatever, to the power L. So it means that you have exponential numbers of ways to create such domain wall. We're not going, it's either like intuitive or not, like we're not going to prove it, it's something that, it's some complicated like random walk problem that people did, but like I think they found like A, C to be like 2 point something, I don't remember. Anyway, this is like a given thing.
Actually it's 2.7 something.
Maybe. But for us is just a number that is not of order of the size of the system, right? Like C is just a number to the power of L. So now when we're going to calculate the free energy,
What is the name of this constant?
what?
This constant have name?
Not the I'm familiar with. It's just
Okay.
a number. So
there is a problem here, because it's supposed to be T was S, and now you enter log to the equation, so it needs to be
yeah,
log.
I'm sorry. This is not S. This is
Log.
the number of states. This is, I said that's the number of possibilities to create such a contour. So
Okay, so you need
yeah.
to add log.
sorry, so that's going to be logarithm of that. So this is L log C. So we have L in the first term and we have L in the second term. So we can take it out. So we have 2J minus T log C. And we said that C is just a constant of order 1. So there is no problem at all to have some critical temperature that gives the distance will give us 0. So we do have a phase transition for final temperature.
Just a
So, okay, so in general, we can have phase transition in dimension 2 and up. This can also be generalized for higher dimension. So now the question is, how can we destroy this phase transition? So what happened if, so some guy came and asked what happened if we add a random field to the system. So now the Hamiltonian going to be, so we have 1j si sj minus hi si. So hi, see that is random variable that's taken from some distribution that follow hi, the mean value of the field equals 0. So, for example, the Gaussian distribution, which is, I think, the most common one to use. So why should a random field, if the field overall is 0 on average, why should it destroy the phase transition? So let's look at the system, again, two-dimensional system. So we have, so we look at specific case where hi equal to either plus or minus epsilon, where epsilon is just a number that's very small compared to the coupling. So this is like a weak random field. And the probability to have epsilon or the probability to have minus epsilon is equal to half. So we have half of the spins field random field up and half of them field down. So I'm going to draw like the random field. So let's see if we need more color. So we have something like before. So spin up. So we have this domain with spin down in the middle, and in general, if we look at like the distribution of the magnetic field in the system, so some going to have minus, some going to have plus, like randomly plus plus minus plus minus plus, and then we look at the case that is very rare, but in a large enough system it can happen, that you have this domain in the middle where all of those spins fill a magnetic field with minus, and everything like on the boundary is going to be like either plus or minus randomly. So basically what happened, you have a random field system and you have this some cluster in the middle that happen to have like a group of spins that all feel the same magnetic field. So in a random system that can happen. Okay, the system is clear.
אז בעצם את אומרת שהמינוסים פה זה השדה שהיא מרגישה והספינים זה...
Yeah, you have the spins and you have, so you have the spins which is similar to before, but the important part is the magnetic field. So
Before it, we not have the magnetic field. Before this, we not have the magnetic field.
right, now we add the random field. So the claim is that if I have a cluster of like that's like domain that's large enough where all of the spins happen to feel the same magnetic field, the energy that takes to resist that magnetic field will overcome the energy that takes to hold the domain wall from flipping. So you have all of this, the rest of the systems, they all spin up, and you have some domain with spin downs. And like normally we know that they will also going to flip and align with the rest of the spins, but in that case they feel magnetic field that like may or may not keep them in that case. So we want to find out, is it going to happen? Is it going to prevent the system from going through a phase transition? So what we want to do, we want to compare the energy resulting from the magnetic field and the energy resulting from the interaction on the boundaries and see which one will win. So let's define two types of energy. One I call E bulk, which is the energy from the magnetic field, and the other is E wall, for like the domain wall. So let's start from E wall. We're going we now go in like general dimension. So let's say general dimension. So the energy on the wall is like similar, like what we did for the two-dimensional case, but for general dimension. So it's not affected by the magnetic field. So it's going to be equal to 2J L D minus 1. Because if I go to dimension D, the length of the domain wall is going to be in dimension D minus 1. So if I'm in 2 dimension, it's going to have 1 dimension. If I'm in 3 dimension, it's going to be like a box, so it's going to be 2-dimensional, and so on. So this is L to D minus 1.
D is dimension?
Yeah. So let's keep everything like approximately. Okay, so what about the energy of the bulk? So it's basically the energy of just the sum of HI multiplied by the spin, right? That's the part of the magnetic field in the Hamiltonian. So we know that all of the spins are aligned with the field within that domain. So it's just going to be sum over HI. But now we need to take into account that
There is a mix because all of them are down.
yeah, it doesn't matter. We look at the difference. So, because what we're going to compare, we don't compare that case to the case where like, so either all of the spins up or all of the spins down. We compare that to the case of like a normal case in the system. So if I compare that part of the system to that part of the system, so to like I don't know if normal is the right word, but yeah, let's call it normal. So we compare the case of all of the magnetic field is have minus signs to the case where like, you know, some have plus and some have minus. So this is like, again, we're not going to go through the derivation because it's not that trivial, but it's like if you think about like the central limit theorem, so you have a sum of random variables. So we know that that thing going to like square root of the number of variables that you have. So this is like it's again like a random walk problem or something. That you just have a set of random variables, and you look at how that thing distributes in the system. So this is going to be proportional to. So let's use epsilon from the size of the field. Multiplied by square root of n. So n going to be the total number of spins in that domain So we know the size of the domain boundary is L. So this is going to be epsilon L d over 2. So the volume is L to the d. We took square root, so d over 2. So those are the two types of energy we have. Okay, so now we want to compare them. So it's you agree that that's what I'm supposed to have, sum over all the fields in that regime compared to like a common case. So for a random variable in general, sum over all random variables, if n is large enough, is going to go like square root of n. This is like central limit theorem. So again, like this is all something that like I think Ido probably went through like in a bit more detail, I hope, but it's just important for the. So let's compare E back to E wall. So we look at the case that like L is a very large number, so we don't really care about the coefficients that multiply it. We just care about the order of magnitude of L. So we compare LD minus 1 to LD over 2. So those two are going to be of the same order where D equal 2, right? So it's kind of similar to what we did with the long-range interaction. We have two cases here. So if T is smaller than 2 and T larger than 2, so if T is larger than 2, it means that the energy from the domain wall overcome the energy from the bulk. So we're still going to have phase transition, even that we have this magnetic field. So we have, let's say, have phase transition. For the smaller than 2, the energy of the bulk will overcome the energy of the wall, and we're not going to have phase transition. So no phase transition. And again, the case of D equal 2, which is always the most problematic thing, it's not going to be included here. Because you see that for D equal 2, this is like not very clear case. So I'm just going to tell you that this is going to be included in the no phase transition case. So this is actually going to be the only one that's excluded, because we know that for like D equal like smaller than 2, we're not going to have phase transition anyway. So the only case that this is not going to affect the system is for D equal 2. So that's the overall. And now let's solve problems.
די זה לא מספר ממדים של הבעיה. די זה לא מספר ממדים של הבעיה.
כן.
אז אנחנו בעצם רוצים לבדוק בכמה ממדים נמצא השריג שלנו?
Yeah, you're going to have like if you have like 3-dimensional Ising model or 2-dimensional Ising model, you're going to behave differently. So this is like a general.
אז רגע, אם אני כבר מראש יודע מה הבעיה שלי, אז מה אני צריך לפתור, מה אני בדיוק פותר פה? אם אני יודע כבר שאני צריך לשחק תחילת המדעי, אז אני יודע אם יש לי מעבר.
No, but if I say you have a question given 3-dimensional Ising model with random field, and I'm asking you, are you going to have a phase transition or not? So this is the answer.
אוקיי, אז בזמן כאילו מפתח פה, אני מבין, קיבלתי את הבעיה, אני כבר יודע ישר אוטומטית מה התשובה.
Is that a problem?
לא יודע, אז אנחנו יכולים לפתור עכשיו, כאילו.
Let's see.
אוקיי. ואיפה נכנס לטמפרטורה?
We didn't talk about the temperature because we didn't talk about the entropy, because if the energy from the bulk overcomes the energy from the wall, it's also going to overcome the entropy. So we don't care about that. We just compare the energy.
אז איך בדיוק מתבצע מעבר פאזה, אם כאילו אין איזה משהו שאנחנו רוצים לשנות?
You're still going to have temperature. We just don't say what it is. We don't care about the value of the critical temperature. We just say this. So, so let's solve question from last year exam. So this is question 3, 2023B. So you're given a three-dimensional system. So 3D ferromagnetic system. Ferromagnetic interaction, you have a coupling coefficient J, and the system is subjected to some random field. So you have random field that's function of I, J, and K, which correspond to the three dimensions of the problem. So it's like the index in the X, Y, and Z direction. So this is like X, Y, and Z. It doesn't matter for the solution, but just the picture. So the random field is given by -1 to the power of I plus J plus K, multiplied by some unit of field epsilon, where epsilon was much smaller than J. And the question is the system going to undergo a phase transition or not in the final temperature? So we had two conditions. One was like a hidden assumption. So one relates to the dimension. So we are like in D equals 3, which is good. We can use this argument. And the second one was that the mean value of the field is 0. Otherwise, we couldn't use the energy that we used. So the question that we actually asking is the mean value of that H is equal to 0. Okay? So what do you think?
No.
Okay, so I, J, and K are the indices of on the grid. So each one of them go from 1 to, let's say, n. Just call it like n or infinity, etc. So if you look at I plus J plus K, it's going to be equal to, so if we started, we can also start it from 0, it doesn't matter, it's just the index. But even if we start it from 1, it's going to be, the minimum value going to be 3. And then the next one going to be 4, and then 5, and then it just all of the natural numbers, basically, starting by 3. So half of those numbers going to be even, and half of those numbers going to be odd, because that's how numbers work. So if you look at H, -1 to the power of something that's half times odd and half times even, going to give us half times -1 and half times +1. So this is going to be minus epsilon plus epsilon if you're going to sum overall the thing. Minus epsilon plus epsilon and so on. So it's going to change sign every time. So this is the sum of I, J, and K. We assume that the number of spins in the system is large enough, it's practically infinity. So if you like you have enough, so it wouldn't matter if you finish with minus plus. So the question is like, is that symmetric from like the summation point of view, and we see that it is, right? So this is overall going to be equal to 0. So we do have phase transition. Yeah, the phase transitions questions in tests are usually like a yes or no questions that like you need to explain, but like the answer is basically like is there or no phase transition. So you can always guess.
אז בגלל שהסכום של הפונקציה הזאת שווה ל-0, אז
Yeah, because we ask.
phase transition.
Yeah, because we ask if the mean value of h is 0, because we have two conditions, one of the dimension and one of the distribution. So it's basically the sum over the total number of spins, but like if the sum is 0 or the average is 0.
מה המשמעות של ה-XYZ הזה שנשאר שם?
It's the coordinates. You have three indices because you have three dimensions.
זה השדה רנדומלי? זה לא שדה רנדומלי, זה שדה שהוא מאוד מאוד יש לו פונקציה מוגדרת.
No, but it behaves like it's random field.
לא רנדומלי.
It changed signs.
אוקיי. רגע, אבל למה זה מתחיל מ3? זה לא מתחיל אולי
Because you start the indices from 1. You can start it from 0 and then it will be 0, 1, 2, 3.
אז כאילו, את אומרת שפה אין קסים. ולמה איך לעשות את הצפיפות? למה הצפיפות הייתה קריטית לנו פתאום? לא הזכרנו את זה לפני כן כשעבדנו.
איפה הצפיפות?
לא יודע, את אמרת שיש פה, שיש לך שני משתנים שרלוונטי כדי לקבוע יש מעבר אחד לצפיפות.
No, I said that you have dimension and you have the mean value distribution, so you have the mean value of h.
אוקיי, אז
To have
לא ציינו לפני כן את המין value כשעשינו את הניתוח.
we did, but very briefly because it was a hidden assumption when you calculate the energy. So going to have phase transition. So 1, you need to have d larger than 2 in the case of random field, of course, in general, and 2, which is the mean value of h, have to be 0. So those are the two conditions of that in remarkment.
אבל היינו יכולים להתחיל מ-0, אז זה היה שווה 2. 2, 3.
It's still okay, it's still going to switch sign every time.
Wasn't it the exact opposite?
Hmm?
And when d is bigger than 2, there is no phase transition? There's no phase transition?
There is a phase transition if d is larger than 2.
There is phase transition?
Yeah. So usually we have phase transition for d larger or equal to 2, but in the presence of random field, it's only going to be if d is larger than 2. So like the only excluded is the d equal to example.
אני לא הבנתי למה, אבל כאילו יכול להיות שווה 2. היינו יכולים להתחיל מ-0, ואז המינימום היה 2, אז זה לא היה מתאים.
If you start the index from 0, okay, so this is going to be.
מתחיל מ-2, אז זה חייב להיות.
Why? You start from 0.
אוקיי. אז זה בכלל לא
So you
מתאים.
have 0, 1, 2.
זה בכלל לא מתאים.
Why?
כי זה לא גדול מ-2.
No, this is no. The dimension is given.
אוקיי.
From here to like all of this question is only referred to that. Like if you solve this in a test, you need to say, oh, the question say it's three-dimensional problem, so we can use input and argument, etc. So, and then like you need to show that.
So for 2 dimension it's not work.
Yeah.
Less.
Yes, but I don't think they're going to give you 2 dimensions because I think he taught until like last year that it's also work for 2 dimensional, and then we found a paper that showed that it's not. So I don't think he wants to give that as a case. It would be a bit, yeah, but basically that's the answer.
איך אנחנו יודעים שיש זוגות, כאילו, של האפסילונים האלה, שלא יישאר איזה...
Oh, that you not have like, you're not going to have like one epsilon left. That like you have.
Yes.
Yeah. So because epsilon is very small and the system is very big, this is like negligible.
אז אני...
So like it's only going to be a problem if like we see in another example when it's going to actually be a problem. So we have like two more cases. So this is case one, and we're going to solve two more.
יש כאילו, אבל תגיד את זה כמו שנגיד סכמות אוילר, שכאילו מראים שטורים לא בהכרח מתכנסים וכל זה כשפלוס מינוס
אתה מקבל חצי
But that's the same. It's not like 1 over n or something. You have plus and minus epsilon. It's always the same thing.
זה לא חייב להיות מוחלט.
גם רוצה שזה יהיה כזה.
Yeah, you talk about case that you have like 1 over n minus 1 to n or something like that. So this is like, it's either like converge or not, but that's not the case. We're not going to give like stuff like that. So the second case, you have h of I, j, and k equal to, again, minus 1 to the power of modulo of I plus j plus k with 2 functions. So
Is this the exact same thing?
it's basically yes, but wait. So what's the modulo function says? So if you have like a, you know how modulo works, right? If you have like
One
a,
or zero.
yeah, in that case it's either 1 or 0. So you have like
So it's
the
exactly,
residue and you have like,
so it's exactly the same.
yeah, so we know that I plus j plus k, it's just a series of the natural numbers, basically. So half of the case they're even, half of the case they're odd. So the modulo is going to give us half of the case 0 and half of the case 1. So this is going to be again minus epsilon, epsilon, minus epsilon, epsilon. So we're going to switch because of the symmetry in the parity of that argument here. It's going to switch sign every time. So this is overall 0. So this is a very similar. Okay, and the last case. So here we have a modulo function again. But this time, I plus j plus k modulo 3. So now it's a bit less.
Now you have
So
0, 1, 2.
Yes,
but
so
0, 1, 2, so 2/3 of the time will be positive and 1/3 of the time will be negative.
exactly. So this is going to be 0, 1, 2, 0, 1, etc. So it's not going to be exchange between 0 and 1.
And over 3 epsilon.
So sum of IH, IJK going to be like, so we have like epsilon, minus epsilon, 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 minus epsilon. So you understood. So now you have something that breaks the symmetry. So you're going to have, for any minus epsilon, you're going to have 2 plus epsilon. So this is overall not going to get to 0.
Yes, and over 3 epsilon.
כן, אבל you say what epsilon is so small.
Yeah, so if you have 1 epsilon, but this is going to give you something of the order of n. So yeah, like n over 3 or something. Yeah. And n is already like a very big number. So the good thing about those questions is that if it's like, if they give you something a bit confusing, you can always just start to write the numbers and see what you get. Like it's a few minutes and that's it. And you see if you get something that look like symmetric or not. It's not a very, you know. Okay, so I have one more question left. It's not very long, so we can do it, and that will be it. Okay. So this is from 2015. Okay, I didn't write if it's A or B. So I think it's A. I'm not sure. What question two? So given a three-dimensional hot model. Where sigma I equal to 1, 2 until Q. So this is similar to something we saw before. So the Newtonian is given by minus J, delta of sigma I, sigma J, minus sum of I go from 1 to n, and L go from 1 to Q. So L is summation over all the possible values of Qi. H, I, L, and delta sigma I, L.
האינדקס האחרון, עכשיו 1, 2, מה האינדקס האחרון? Q?
Q. And HIL equal to plus minus epsilon with equal probability. So, question 1, what's going to be the ground state energy of the system where we don't have external field? So, what is the ground state if H equals 0?
פשוט שכולם יהיו באותו כיוון, כי אז
Exactly, so all of the spins align in the same direction, all of the deltas are 1, so big ground state equal minus J n.
I not understand this.
ויש כאן ניגוד
Can you explain again?
Yeah, so if we don't have external field, this thing is 0, so we only have that. If the spins align in the same direction, the delta gives 1. So we assume that in the ground state, all of the spins are in the same direction, because it's going to minimize the energy, because it's a ferromagnet, which it did not write here. So all of the deltas are 1. We have sum of 1 multiplied by J for n spins in the system. So I multiply the J.
N is number?
The number of spins, sorry. So this is like number.
אז צריך גם להכפיל ב-Q.
No, because this is just the energy. Now the Q we're going to take into account when we talk about the degeneracy. Because either all of the spins, this is like the direction of the spin. So either all of the spins are in direction 1 or 2 or 3.
I mean J, not L. J goes to N2.
Sorry.
I ו-J הולכים ביחד ל-N?
Yeah, this is like the
אוקיי.
nearest.
כי לא רשמת N מעל J.
Yeah, they're all both. Yeah, but like no, it's not the. No, because it's like nearest neighbors interaction. So
מה רשם? N נקודה N?
nearest neighbors. So they asked about the ground state and the degeneracy. So we see that we have Q options, so the degeneracy is Q. So now the second part of the question is with that external random magnetic field, are we going to have a finite temperature phase transition? So this is the question that we saw before. This is like, I think you can answer that like the long way and the short way. So first of all, we see that like the mean of h is clearly 0 because it's half the time up and half the time down, and the dimension of the model is fine. So the only thing that's different is that the type of the interaction. So if we look at like the energy of the bulk and the energy of the wall as we did before, we see that we don't really have anything different. So if we look at E wall, the only difference is that instead of interaction of Si and Sj that we had in the Ising model, we have a delta, which means that like it's just going to give us factor 2 in the energy, because in the Ising model, if you have spins that are like not aligned, you have a minus j, and here you have 0. So instead of 2jl, you have just jl. But because this is just a factor, it doesn't matter. So the order of magnitude of L is still going to be the same.
What is the question?
The question is the system undergo phase transition, final temperature phase transition. Okay, so we are in dimension 3, so this is going to be L to the power of 2. So now let's look at the expression of the field. So again, this is very similar to what happened in the Ising model, but we have two summations here, so it can look confusing. But if we look at like the simplest case where sigma I can only have 2 values, so this is going to be, let's say, q equal 2, okay? So this is going to be sum over I, and then hi1 plus delta sigma I1 plus hi2 delta sigma I2. So for each option of sigma I, the delta function is going to be either like 0 or 1. So if we have a bulk where all of the magnetic field is in the same direction, so let's say they're all plus, and all of the spins are also in the same direction, so let's say they're all up. So this is again going to be something that goes like sum over hi, right, or hi1 in that case, because this is just going to give us 1 for whatever we take. So if we have additional sum over q, like it doesn't matter, it's just going to give us eventually, it's going to give us some factor, but we still have something that's proportional to sum over all of the magnetic field. So in that case, E bulk still going to be proportional to L d over 2, because the general scaling is exactly the same as what we saw for the Ising case. So this is in that case L 3 over 2. Yeah, because the equals field. Why that one is equal to that, or why that one? The energy. Okay, so I want to show that the contribution to the bulk energy of that domain, where all of the spins in the same direction with all of the field components. So I want to show that this one is exactly the same as we saw for the Ising model case. So for the Ising model, we have that, and we said, okay, if all of the spins align with the magnetic field, the contribution to the energy is just going to be the sum over all of the magnetic field components. And here, if all of the spins align with the magnetic field, this is going to be, so this is going to be 1 only when they're like both in the same direction. So it's still going to be sum of HIL, even if you have additional sum over L. So the sum over L is just going to give me a factor. So this is from order of magnitude with the size of the system. It's still going to be the same. It's still going to be the same as what we claimed for the Ising model case. It's still going to scale the same with L.
רגע, אבל יש לך כאילו את הדלתא, אז זה לא הולך קצת להוריד לך דברים?
No, but the delta are going to give you 1 if they're aligned.
אוקיי, כאילו אם כולם באותו כיוון, אז ככה זה לא משנה, אוקיי? זה סיגמה I עם L, לצורך העניין. או שזה אולי סיגמה...
Yeah, so sigma I is equal to L, but HI is also L. So if that L and that L are the same,
רגע, אבל L זה לא ספין.
L is like direction of spin. If it was like a simple case, so sigma I would be like plus minus 1, for example. So you had like HI for like sigma I equal plus 1, and then another H for sigma I equal
אבל סוכנים פה על L. סוכנים פה אבל על L מ1Q.
Yes.
כן, הדלתא שלך תקבל ערך 1 אחרת 0 בערך מקום 1. אז כל הסכום הזה על L הולך בעצם.
Right.
אז כאילו, לא ממש צריך אז רגע, אתה רוצה לסכום על I, אז כאילו, מקבל את זה. וזה הופך להיות N, נכון?
Okay, so we all agree about that part, I hope. So we take the equal strip, we put here, and then overall we see that the energy of the wall overcome the energy of the bulk. So we do have a final temperature phase transition. Okay?
אבל זה לא תשובה סופית.
Well, the finite answer is yes. Okay, so that was it for phase transition. So this is for like the no-yes questions of phase transition. I think either next week or the one after we're going to talk more about what actually happened in phase transition. That's going to be actually more fun. Okay, so that's it.
אז הסיבה שזה בעצם קרה זה משום שהאי-וול יותר גדול מהאי-בל. יש לו בעצם העדפה לסדר בעצם את הספינים כדי לשמור בעצם שהכל יהיה אותו ספין, במקום שכאילו לצורך העניין ש...
Yeah, this is like more expensive to him than that.
אפשר לעשות גם את 2, אבל
קפסטוק. לא, הייתי צריכה לאפס את הקפסטוק במוח. את 2? אוקיי. So, את האנרגיה של ה... אוקיי, אז יש לנו, כמו קודם, איזושהי מערכת כזאת, בשלושה ממדים, אבל איזה מידה. ואני רוצה לקבל, מה שמעניין אותי זה איך האנרגיה שנובעת מהדומיין וול, ואיך האנרגיה שנובעת מהשדה המגנטי, איך הן תלויות ב-L, ש-L זה איזשהו היקף של הדבר הזה. ואז בעצם אני רוצה לדעת איזה אנרגיה, ואז אני רוצה לדעת איזה אנרגיה בעצם מנצחת, כי האנרגיה שיותר גדולה היא בעצם, כאילו אם יותר יקר לי אנרגטית להחזיק את הספינים במצב שיש לי פה ספין דאון ופה ספין אפ, אז המערכת תעבור face transition, ואם האנרגיה של הבעל, כי האנרגיה של להתנגד לשדה תהיה יותר גדולה, אז המערכת תישאר במצב הלא מסודר הזה, כי זה יהיה כאילו יותר נוח. אוקיי, אז האנרגיה של הוול, אז כל מה שמשתנה פה ביחס לאייזנג מודל זה שהאינטראקציה היא עם דלטה ולא עם SI/SJ. נכון?
למה?
באייזנג מודל יש לנו פה סכום, SI/SJ, ופה יש לנו דלטה של סיגמה I, סיגמה J, או סיגמה ו-10. So, הפער באנרגיה בין זה שכל הספינים בתוך הריבוע הזה הם up לבין כל המצב שהספינים הם down, זה בעצם המספר הספינים שנמצאים על השפה כפול הערך האנרגטי של להפוך כל אחד מהספינים, שזה יהיה נתון על ידי הדבר הזה. אז סך הכל זה בעצם יהיה J כפול L2 בחזקת D, D פחות 1, כמו שהיה לנו במקרה של אייזנג, של D פחות 1 זה כאילו האורך של זה בממד D. זה מספר הספינים על השפה. נכון, בגלל שזה תלת-ממדי, אז בעצם כאילו יש לנו מרחב תלת-ממדי, ויש לנו פה בעצם קופסה. יש לנו ספינים בתוך הקופסה ובחוץ הקופסה. אז L יהיה איזושהי יחידת אורך, אז בעצם יהיה לנו L בריבוע, משהו שיש לו יחידות של מטר בריבוע, שזה בעצם הגודל של הקופסה, השטח פנים של הקופסה.
כן, אבל זה D מינוס, לא הבנתי, רשום שזה D מינוס 1.
כן, בממד הכללי זה היה D מינוס 1. במקרה שלנו, יכולתי לכתוב ישירות את זה, פשוט רציתי להראות שזה אותו דבר כמו מה שקיים.
יש שאלה?
כן.
לגבי התרגיל הראשון,
הראשון?
כן, הגשתי אותו פשוט.
אוקיי.
סתם רציתי עם הבדיקה היא כל שבוע, או סתם שאני...
כנראה הבדיקה תהיה קצת יותר מאוחר, כי פשוט קורס נורא מוזם ככה, אבל גם הבדיקה כנראה לא תהיה מאוד מאוד יסודית, אז כאילו מבחינת, אם אתם רוצים לדעת האם צדקתם בדברים וכאלה, הייתי פשוט משווה עם פתרונות ולא
ונגיד התרגיל השני, רק לשאלה ראשונה, סעיף 3, כאילו עניתי על הכל, לא הספקתי בסעיף 3 רק.
זה הסימולציה, נכון?
כן, הסימולציה, כמה נקודות פחות יותר מכל התרגיל?
הייתי אומרת לחלק למספר השאלות כזה, אבל כאילו פשוט תגיש עכשיו, תשלח לי מייל, אני אפתח לך את ההגשה ותעדכן את זה.
לא, אבל נגיד, אם אני עושה שיקול לעומת השקעה...
זה 10%, זה רק 10%. 10% תרגילי.
10% תרגילי בית טיפול?
לא, ספציפית שאלתי על סעיף.
כן, אז בוא נגיד בשאלה הראשונה יש 3 סעיפים, בשאלה השנייה גם יש איזה 3-4 סעיפים, אולי 10 נקודות אם אני ממש אהיה במצב רוח רע.
כן, אבל אם נגיד...
זה מתוך התרגיל.
כן, אבל אם אני הגשתי, כאילו התחלתי לפתור, ואז כאילו פשוט זה לא סוף.
אז חצי מהנקודות, 5 נקודות. משהו כזה, אני לא מאוד סגורה.
כן, זה בריבוע.
אוקיי. אז E-Wall, אנחנו מסכימים שזה הולך כמו על בריבוע. עכשיו E-Bulk. אז בעיקרון E-Bulk נובע מהאיבר הזה. אז זה בעצם האנרגיה שדרושה כדי להחזיק את כל כדי בעצם להפוך את כל הספינים האלה, לגרום להם להתנגד לשדה. אז זה אומר שכל הספינים הם בעצם צריכים להפוך כיוון ביחס לשדה, כי אמרנו שהם כולם באותו כיוון כמו השדה. אז הדבר הזה יהיה שווה 1. אז בעצם יש לנו סכום על I, HIL. בעצם כמו שאמרת, הדבר הזה בעצם גם מתבטל בגלל הדלטה. אז בעצם כל מה שיש לך זה פשוט סכום על השדה המגנטי שיש על כל אחד מהספינים בתוך הקביעה הזאת. וכמו שלא הראינו, אבל כמו שטענו קודם, הדבר הזה הולך כמו שורש של מספר הספינים כולל. במקרה שלנו, כי אנחנו בתלת ממד, זה יהיה L בחזקת 3/2.
אבל למה זה...
זה כאילו פרופורציונלי לשורש הנפח.
למה אבל זה עוד פעם הופך לאחד, האל?
אוקיי, תחשוב שיש לך, עם כל הספינים וכל השדות המגנטיים הם באותו כיוון, אז עבור סיגמה I, ששווה לאיזשהו ערך של סיגמה I, בין 1 ל-Q, אז הסיגמה I תמיד יהיה שווה כאילו הכיוון של... מוח שלי סלט. אז סיגמה I תמיד יהיה שווה כביכול L. אנחנו כאילו סוכמים על כל האופציות שבהם L מיושר עם הכיוון של הספין. נכון? כאילו במקום שיהיה לי שפשוט הספין מוכפל בכיוון של השדה, אז פה זה או 0 או 1, כמו איזשהו מספר. אז בסך הכל, אם הוא בכיוון של הספין, אז הוא ייתן לי, של השדה, הוא ייתן לי 1, אם הוא לא בכיוון של השדה, הוא ייתן לי 0. אז בסך הכל אני נשארת עם סכום על כל השדות המגנטיים, על כל אחד מהספינים.
ואיך את יודעת שזה באותו כיוון? זה נתון?
זה בעצם הטיעון שאנחנו עושים בכללי כשיש לנו סדר רנדומלי. אנחנו אומרים בוא נניח, כאילו כל מצב אחר שאני אעשה, בוא נגיד אם אני אוסיף פה ספין דאון, הוא כאילו יחמיר את המצב, אז זה כאילו המצב, אני משווה שני מצבים קיצוניים, שאו שכל הבא כזה up או שכל הבא כזה דאון.
כאילו יעלה לך כמה שתגיעי כמה שאתה קרוב למצב היסוד.
כן. אז בסך הכל אנחנו מקבלים L בשלושה חצאים, וזהו, אנחנו רואים ש-L בריבוע יותר גדול תמיד מ-L בשלושה חצאים. האנרגיה של השפה מנצחת, זה אומר שיותר יקר לי להחזיק את הספינים במצב שהפוך לספינים שמסביב, מאשר להתנגד לשדה המגנטי. זאת אומרת שהמערכת תהפוך את הספינים, ובעצם כל הספינים יהיו באותו כיוון, ואז בעצם מעבר פאזה שלו.
אבל אם את כבר הפכת את כל הספינים כדי שתגלו שדה, כאילו, בדיוק מה שקורה, זה הסיבה שיש לך את הדומיין וורס, מכל אלו בעצם נגדים של היחידות.
לא, אני מתחילה במצב שכל השדות המגנטיים בפנים הם באיזשהו כיוון, וכל הספינים הם באותו כיוון של השדות המגנטיים, וכל הספינים בחוץ הם בכיוון ההפוך. זה כאילו תנאי ההתחלה שלי. ואני אומרת, אם אני רוצה שיהיה לי מעבר פאזה, אני צריכה שהספינים האלה יתנגדו לשדה המגנטי שבפנים. שזה כאילו, אולי הם יעשו את זה ואולי או לא.
לא צריך לחשב את המין, זה מספיק לראות שזה...
כי נתון שזה חצי מהפעמים אפסילון וחצי מהפעמים מינוס אפסילון, אז זה כאילו טריוויאלי להגיד שהממוצע הוא אפס.
טוב. כאילו אם זה נתון, אז לא הכוונה שאנחנו נגיד...
כאילו מה שנתון מבחינת הניסוח של השאלה, אני לא יודעת אם הייתה בדיוק את הניסוח של השאלה, אבל מבחינת הניסוח של השאלה נתון משהו כמו H שווה פלוס מינוס אפסילון בסיכוי חצי, משהו כזה, אז כאילו אם הייתי פותרת את המבחן אז הייתי מזכירה שכאילו קל לראות ש-H ממוצע שווה אפס, משהו כזה.
שזה, שאנחנו לא רוצים, כאילו, שאת לא רוצה שאני אוכיח שזה אפס בעצם.
אתה יכול להוכיח שזה אפס, אבל זה כאילו חצי כפול מינוס אפסילון ועוד חצי כפול אפסילון ואפס.
זה עשית אומרת שסכום על כולם, זה בעצם המוצא הכולל, ואז זה מגיע שהכל ביחד למוצא הוא אפס. הפנימי בלבד את רוצה, נכון? או שרוצה על כל הספינים שנמצאים בכל השרים באופן כללי?
על הספינים בכללי, כי זה משהו שקשור להתפלגות של H, זה לא משהו שקשור למה שכאילו אנחנו עושים. אם זה מתקיים, אז אנחנו יכולים לטעון מה שאנחנו טוענים. אבל זה כאילו משהו שכאילו מגיע לפני.
אז כאילו, את אומרת שקודם בכלל כדי שאפשר לדבר על אם יש לי מעבר פאזה או אין לי מעבר פאזה, זאת אומרת, הדיון שעשינו פה, אנחנו צריכים בכלל כל לדעת אם בכלל יש אופציה לזה ייתכן, ואז בדקתי באמת את הקטע של מיצוע, לצורך העניין. זאת אומרת שיש
אפשר לדבר על מעבר פאזה במקרה אחר, אבל זה פשוט תצטרכו לעשות עם אחר, זה מערכת... אם יש לך שדה ממוצע שהוא לא אפס, אז זה כבר לא שרירת סימטריה, כי המערכת כבר לא סימטרית מלכתחילה. כל הרעיון של המעבר פאזה זה שיש לך.
אוקיי, רגע, אז בעצם אחרי שעשינו את כל התהליך של הבדיקה של השדה הממוצע הוא אפס והכל, ולמה ניגשנו לזה לעשות את החישוב? אז אם אנחנו בוודאות יודעים שהוא עושה נגד לצורך שרירת סימטריה, למה הם צריכים את המקרה הזה שכאן? הרי אנחנו אמרנו שכשהממוצע שלנו הוא אפס, נכון? וכשאנחנו יודעים שאנחנו בסדר שומע יותר משני ממדים, בוודאות יש מעבר פאזה בטמפרטורה סופית
נכון,
כלשהי.
אבל מה שעשינו זה למודל אייזנג,
אוקיי.
וזה מודל שהוא קצת שונה. אז בגלל זה אמרתי, יש תשובה ארוכה ויש תשובה קצרה. אני ראיתי אנשים במבחנים שגם עשו פיתוחים מאוד ארוכים, אבל כאילו זה לא נחוץ. אני כן חושבת שיש עניין להגיד בכמה מילים של למה זה בעצם אותו דבר. שזה מה שניסיתי כאילו לעשות פה. שכאילו, העניין הוא כביכול שונה, אבל זה בעצם אותו דבר.
רגע, אז בעצם הגישה עם השלושה ממדים והממוצע שווה אפס זה מודל אחד?
זה מודל אייזנג.
מודל אייזנג. ופה אנחנו בעצם מדברים על מודל שהוא לא אייזנג, אז היינו צריכים לעשות את כל הניתוח המלא הזה?
כן, אבל שוב, לא עשינו את כל הפיתוח באמת מאפס כמו שעשינו בהתחלה, רק אמרנו זה אותו דבר.
אמרנו פשוט שהדבר הזה שעשינו פה זה הפיתוח שהיה צריך לעשות. אני רק אציין את הדבר כמו שנקרא את הקודם.
למה אבל זה חצי? לפחות חצי אפסילון?
זה כאילו PI כפול HI, זה כאילו ממוצע.
אוקיי. יש לי עוד שאלה, תרגול קודם, אפשר לשאול?